Okay, so for one say you have questions 5 and 7. For two say you have question number 2 maybe. वो भी वैसे इतना ज़्यादा तो नहीं आप लोगों ने कहा. Only couple of votes in that. But then from the third paper there are more questions. We could start from that. We could start from 4-3 if that's the most difficult, and then we'll do 4-1 and then 4-2. Okay, let's start with that. Okay, so we are doing 3 papers today. Difficult questions from these 3 papers: June 2022, paper 4-1, paper 4-2, and paper 4-3. We're starting with 4-3 first of all because you have more questions from that. Let's begin with this. So from this paper, you're asking about questions 4, 6, and 7. Let's have a look at these 3 questions from this paper. This is momentum. Okay, that means there won't be another kinematics and momentum question in this, probably. 2, 3 is this graph. Okay. All right. This is the first question that we're asking about. Question number 4. It's very similar to that other question. I think it's that one. Yeah. So very similar to the question that we did in the previous class. I think when we did the October-November paper, and we had to find the least value of a force. In this case, we got to find the greatest value of a force. Let's have a look at this. Let's start with this one. Question number 4 from this paper. Okay, so it says the diagram shows a block of mass 10 kilograms suspended below a horizontal ceiling by 2 strings AC and BC of lengths 0.8 meters and 0.6 meters respectively, attached to fixed points on the ceiling. Angle ACB is 90 degrees. There's a horizontal force of magnitude F acting on the block. The block is in equilibrium. Equilibrium means the opposite forces are supposed to be equal to each other. In the case where F is equal to 20, find the tensions in each of the strings. Now, since it's equilibrium, all you have to do is just resolve the forces and equate the opposite forces, right? That's what we would do. We would resolve the forces and equate the opposite forces. Now, how do we resolve? For that, we need the angles. That's why we're given these lengths. So let's use these lengths first of all to find the angles. Let's call this angle something. Let's call this angle theta. Can we find the value of this angle theta? Perpendicular and base, you can use tan. Tan theta equals 0.6 over 0.8, and that's going to give us the value for theta. What does that turn out to be? What's the value of theta? The value of theta that we get from this. Okay, I would really appreciate if I can have multiple people doing the calculation so that we can speed up a little. Because we've got 3 papers to do. It'll take time. 36.9 degrees. Okay, 36.9 degrees or 36.87 degrees, right? This is not the final answer, so we should use more accurate numbers. 36.87, that's this angle. If this is 36.87, what that means is this angle here, that is going to be 53.13. Okay, so we've got these angles. Now that was the only use of these lengths that were given to us, so we can get rid of them now. We don't need them anymore. Let's resolve the forces. We've got weight acting on this block that acts vertically downwards, 100 Newton. There's tension acting in this direction. Let's call that T1. There's tension acting in this direction. Let's call that T2. It's going to be different tensions because it's a fixed point here. The string is not free to slide through this. So we've got different tensions. Let's resolve the forces, resolve the tensions. We've got one component of tension acting towards left, one acting in the upwards direction. If we know that this angle is theta, that was 36.87, then this angle is alternate angle, that's also 36.87. So what are the components going to be? The component on the left side, that's T1 cos of 36.87, and the component acting in the upwards direction, that's T1 sine of 36.87. And then the components of the force T2, what are they going to be? T2 has one component acting in this direction and one acting upward, acting vertically upwards. If this angle is 53.13, we know that this angle here is also going to be 53.13, alternate angles again. So this component is T2 cos 53.13, and the other one is T2 sine of 53.13. We've resolved all the forces. All we have to do now is equate the opposite forces and make two equations. This should equal this plus F, and this tension component should equal this, this plus the other tension component, that should equal 100. We get two equations from that. Left equals right, that gives us T1 cos 36.87, that equals F plus T2 cos 53.13. That's one equation. And the other equation, upward forces equal the downward forces, T1 sine of 36.87 plus T2 sine of 53.13, that equals 100. Now, those of you understand this, that if this is if this length is 0.8 and this is 0.6, the hypotenuse would be 1 using Pythagoras. You could directly use the values of sine theta and cos theta in these places rather than finding the angle. So sine theta, for instance, with respect to this angle, that would turn out to be 0.6, and cos theta would be 0.8. Right? So you could use that you directly input sine theta and cos theta here directly. If you don't get what I mean by this, just forget it. It's okay. Just find the angle and do it not the normal way. You get two equations. Cos 36.87. What do you get from this? Cos 36.87. What's this value? Anyone? This should be 0.8, right? Yes. 0.8 T1. That equals F plus cos of 53.13. That would be 0.6 T2. Sine of 36.87, I think that should be 0.6 T1. And then sine of 53.13, that should turn out to be 0.8 T2. That equals 100. We get these two equations. We solve them simultaneously. Input F equal to 20 here. 0.8 T1 equals 20 plus 0.6 T2. And we've got the other equation there as well. We can make one variable the subject. We can make T1 the subject here. 20 over 0.8. What's that? 20 divided by 0.8. What does that give us? That's 25. And then on the other side, 0.6 over 0.8, that's 0.75 times T2. This is T1 in terms of T2. We can input that in the other equation now. And that gives us 0.6 T1 plus 0.8 into 25 plus 0.75 T2. That equals, oh, that's something wrong somewhere. T1 was equal to that, so that means it's 0.6 into 25 plus 0.75 T2 plus 0.8 T2, that equals 100. We can simplify this. 0.75 into 0.6, that will be 0.45. 25 into 0.6 is 15. 15 plus 0.45 T2 plus 0.8 T2 equals 100. That's 1.25 T2 equal to 85. And that will give you the value for T2. You can see what that turns out to be. 82, 85. divided by 1.25, and that's 68 Newton. That's the value of this tension. Input that in the other equation, and that will give you the corresponding value for T1 as well. That's 25 plus 0.75 into T2, that is 68. And you can see what that turns out to be. 25 plus 0.75 into 68, that's 76 Newton. These are the values of the two tensions that we were looking for, right? T1 is 76 and T2 is 68, and that's our final result. Okay, all right, good, thank you. So that's it. That's the first part, fairly straightforward. We just resolved the forces, equated the opposite forces, and we got the result. Let's move on. Now it says find the greatest value of F for which the block remains in equilibrium in the position shown. How do you think about this now? Let me just copy this diagram there. These are the forces that are acting. How do you think about these problems? Greatest value of a force, least value of a force, when you have an object hanging like this. What did we discuss about it? We would have to input one of the tensions equal to 0, right? That's what we normally do. One of the tensions equal to 0. Now, how do you figure that out? Let's understand that logically. Oh, so they're saying find the greatest value of F for which the block remains in equilibrium in the position shown. Now, where's F acting? F is acting towards the right side in this direction. What happens if F becomes very big? If F becomes too big, what would happen? What would happen to this block? The block will start moving to the right like this, right? If F becomes too large, the block will start moving to the right side like this. When it starts moving to the right like this, let's suppose it comes in this position. This string is going to become slack, the one that's connected to B. So what we do is we say, if the equilibrium is just about to break, what would happen would be the tension in the second string T2, that is going to become 0. So that's what we put there. We say for F to be greatest, the object would just be about to move towards the right side. It'll be in an equilibrium state that's just about to break. When it's just about to move to the right, this tension is going to become 0 because the string will become slack. T2 will become 0 Newton in this case. Okay, this string is going to become slack. And that's all that you have to do here. We've got these same equations as before. Nothing is changing as far as the forces were concerned. The only thing that's different is in the first part, they gave us that F is equal to 20. And now they're asking us for the greatest possible value of F for which the equilibrium remains. So we don't put F equal to that value, 20 in this case. We have to find the greatest possible value of this. How do you do that? Put T2 equal to 0 and see what that gives you. When you input T2 equal to 0 here in both of these equations. Now the second equation has less unknowns, so we can start with that first of all. That gives us 0.61 plus 0 equals 100. And that's going to give us the value for T1. 100 over 0.6, that is 500 over 3, which is 166.67. That's T1. Input that in the other equation, and that will be 0.8 T1. That becomes 166.67 equals F plus 0. And the value of F turns out to be this time 0.8. And that would be 133.33 Newton. Since this is supposed to be our final answer, we say the greatest possible value of F to three significant figures, that's 133 Newton. Okay. We just discussed that. They are asking us for the greatest possible value of F. If F becomes very big, so they want the object to remain in equilibrium, right? They want the object to remain in equilibrium. How would equilibrium break? If F becomes too large, eventually what would happen would be this block will try to move to the right side. So what's that extreme value of F that we can have such that it remains in equilibrium? What's the greatest possible value of F that we can have? That would be when this block is just about to move to the right side. Now, if it starts moving to the right side, let's say it comes here, what happens to this second string, this string? What happens to that? That becomes slack because the block gets closer to the point B. The string was longer than the distance between these 2 points. So the string becomes slack. When that becomes slack, its tension is supposed to equal zero. So that becomes zero. Make sense? Okay, so the right string, that becomes slack. For that reason, we put the second tension equal to 0 Newton. All right, that gives us the greatest possible value of F. That's what we were looking for. That's question number 4. That's one question that you asked about in this from this paper. Then question number 6 from this paper. Let's have a look at that now. Question number 6. Okay, this one. Two particles P and Q of masses 0.3 kilograms and 0.2 kilograms. They are attached to the ends of a light and extensible string. The string passes over a fixed, smooth pulley at the point B. Okay. Masses are shown in the diagram as well. We've got these two inclined planes. P lies on a smooth plane AB. So AB is smooth. The angle is shown there on the diagram. BC, we don't know anything about BC yet, if it's smooth or not. String is taut and the particles can move on lines over through planes. Okay, all right. So the only important piece of information here is that AB is smooth. Everything else is shown in the diagram. It's given that plane BC is smooth. Now, in the first part, they're saying BC is also smooth. And that the particles are released from rest. Find the tension in the string and the magnitude of the acceleration. Whenever they talk about finding acceleration and tension together, that means you're using Newton's second law of motion, right? Because tension is a force, and then acceleration. What connects forces and acceleration? F equals m. That's what we would use here. We apply Newton's second law of motion, both of them individually. We apply that on the particle P and on the particle Q. Which direction are they going to move in? Both surfaces are smooth. In the absence of any other forces apart from weight and tension, the only direction they can move in is this direction, right? So they move in the downward direction. What's the forward force for them? This is the forward force. So let's represent the forward direction. This is the forward direction. What are the forces that are acting? For P, we've got 3 Newton acting vertically downwards. We have reaction, although we can ignore that because the surfaces are smooth. So in smooth surfaces, we don't consider reaction. It's not required, right? What else? We've got tension that acts in this direction. And that's it, right? Let's resolve the weight. There's one component that's going to act in this direction, another component acting in this direction. Along the surface, if you know this angle is 60 degrees, this is also 60 degrees. So along the surface, the component would be 3 sine 60 degrees. All right. And then what about Q? Q has weight acting vertically downwards. That's 2 Newton. There's tension acting in this direction. And that's it. These are the two forces that are acting on Q. What are the components of weight going to be? One in this direction and the other in this direction. Again, we only need the one that acts along the surface. If this angle is 30 degrees, That means this angle is here is also 30. So this component would be 2 sine 30. Let's resolve the forces. Let's apply Newton's second law of motion. We've got 3 sine 60 as the forward force here, T as the backward force for P. So its equation is going to be 3 sine 60 minus T. That equals mass of P, which is 0.3 times acceleration. That's one equation that we've got. And then for Q, what's the forward direction? What's the backward direction? Forward direction is T, and it's also 2 sine 30. We can say T plus 2 sine 30. That equals mass, which is 0.2 times acceleration. Solve these two equations simultaneously. You get the values of T and A. You can see what that turns out to be. Sine 60 is under root 3 over 2. So 3 under root 3 over 2 minus T equals 0.3 times A. And the other equation gives us T plus 2 into sine 30, which is 1 over 2 equals 0.2 times A. T equals 0.2A minus 1 from this equation. Put that in the first equation, and that gives us 3 under root 3 over 2 minus 0.2A minus 1 equals 0.3 times A. Let's solve this equation and see what that gives us. 3 under root 3 over 2 minus 1, that's plus 1. This is minus 0.2A, will go to the other side, become 0.5 times A, and that will give us some value for acceleration. What's the value of acceleration that we get? Value for A, what's that? .19. Minimum 4 significant figures in your working, because you have to use this in T as well now. 7.196. Okay, 7.196. Thank you. Okay, so that's going to be wrong. You lose 1 mark for this. If you write it as 7.19, you lose 1 mark because that's not correct rounding off. So you write this number first and then you round this off to 7.20. And now you put this number in the other equation, 0.2 into 7.196 minus 1, and that will give you the value for T. You can see what that is. 0.4392, so that's 0.439. This is the final answer now. We can write the final answer is correct to 3 significant figures, but anything that can still be used, that is still supposed to be used in another part, you write that to minimum 4 significant figures before rounding that off. All right, that's part A. Really straightforward. You just resolve the forces, equate the opposite, and then used Newton's second law of motion to find that acceleration and tension. Okay, let's move on now. All right. Let's have a look at the next part now. Question part B of this. It's given instead that the plane BC is rough. A force of magnitude 3 Newton is applied to Q directly up the plane along a line of greatest slope of the plane. When do we consider one single system? When you're applying Newton's second law of motion, I would recommend always do it separately. That makes it easier. It can also be done by considering it as one single system, but it's mostly safer. It's less prone to errors if you do it separately. In some work energy power questions, we do use the whole system. That makes it more efficient. But in Newton's second law of motion, it's very rare that you would prefer using the complete system. That can make you do plus minus errors, but it can be used if you want to use it. But I do not generally recommend it because of the careless errors that you can end up doing using that. Okay, let's look at part B now. So it's given instead. That plane BC is rough. That means the first part is no longer relevant now. Whatever was given there. The second part says BC is rough. A force of magnitude 3 Newton is applied to Q directly up the plane along a line of greatest slope of the plane. Okay, so along the surface, there's a force applied 3 Newton to Q. Find the least value of the coefficient of friction between Q and the plane BC for which the particles remain at rest. Again, least value of something. Generally, it's about a force, but in this case, they're asking for the least value of Mu, coefficient of friction, you use limiting equilibrium, right? To find the extreme value of something, when you have friction involved, you consider limiting equilibrium case. Okay, so that's what we will be using here. First of all, let's represent all the forces that are acting. There's a 3 Newton force applied to Q directly up the plane. Let's represent that here on the diagram. Now there's another force that's acting in this direction. That's 3 Newton. Okay, that's for the second part. And because of this, what happens is least value of the coefficient of friction for which the particles remain at rest. Okay. Now, first of all, let's consider the forces acting on both ends, on both sides. So we have 3 Newton that's acting in this direction. And in the other direction, we've got T acting here. If it's equilibrium, this T is supposed to equal this, right? These two are supposed to be equal to each other. 3 sine 60. So in the upwards direction, the total force that we've got is 3 Newton. In the downward direction, if it's at rest, the force right now, before considering friction, is 3 sine 60 and 2 sine 30. Let's evaluate this to see in which direction there is a greater total force. 3 sine 60. Make sure your calculator is in radian mode for your mechanics paper throughout. Angle unit degrees. Okay. 3 sine of 60 plus 2 sine of 30. In the downward direction, we have a force that is 3.5 Newton acting overall in this direction. Which one is bigger? 3 Newton is smaller. This is bigger. That means the particles are going to try and move down the plane because of that. Okay, the particles are going to try and move down the plane. So where does friction act then? Friction acts up the plane for this reason. So the direction of friction, therefore, is also going to be this. Now, what's the least friction that is required? What's the least friction that is required to keep the particles at rest? That's what we want to find out, right? Least value of mu means the least roughness between the object, the least friction. That's what we're looking for. So all you have to do is, first of all, equate the opposite forces. Let's see what we get from that. First of all, for particle P, we've got the same two forces that are acting, T and 3 sine 60. So for P, we can say T is equal to 3 sine 60. And that gives us T equal to 3 under root 3 over 2. We're talking about rest, right? That's equilibrium. So we equate the opposite forces. For Q, what are the forces acting in Q now? Since we also have friction involved now, we have to consider normal reaction as well. We've got normal reaction acting in this direction. The component of weight acting in this direction is 2 cos 30. Now, R should equal 2 cos 30. R should equal 2 cos 30. Let's write that down here. R equals 2 cos 30. And that's 2 under root 3 over 2, which is under root 3. And 3 plus F, that should equal 3 plus F should equal T plus 2 sine 30. Let's make that equation. T plus 2 sine 30, that should equal 3 plus F. Right? That's another equation that we get. Now, let's simplify everything and see what that gives us. T plus 2 into 1 over 2 equals 3 plus F. Since we're looking for the least value of mu, we consider the limiting equilibrium case, right? Whenever we're looking for extreme values of something and there's friction involved, we consider limiting equilibrium. Okay? Because that's the extreme case of equilibrium. That's what we have to consider. If it's limiting equilibrium, that means F equals mu I. So in place of F, we can replace, you can write mu times R. Okay, now we've got everything that we want. 3 under root 3 over 2 plus 1, that equals 3 plus mu, which we have to find out, into r, that's under root 3. And that should give it the value for mu. You can see what that turns out to be. 3 under root 3 divided by 2 plus 1 minus 3 divided by under root 3. And that's given me 0.3453. That's 345. And that's the result that we get from this. That's the value of mu that we were looking for. Make sense? Any issues with this? This is 4-3 that we're doing first of all. We're doing 4-3 first of all. November 2022, paper 4 reading. June 2022, paper 4 reading 3. Okay, that was part B. Any problems? Any questions, anyone? Okay, good. Let's move on. Now, the next question that you asked about from this paper is question number 7. Okay, so that's the last one that we're doing from this paper. And then we move on to 4-1 after that. There are 2 questions from that paper, and then maybe 1 from 4-2. Okay, let's do this one. Question number 7 from this. It says a particle P moves in a straight line through a point O. The velocity V is given by this after passing a point O. So time is starting at the point O, right? At O, time is equal to 0. B and C are positive constants. At time equals 5, the velocity of P is 0 and its acceleration is minus 13 over 12. Show that B equals 9 and find the value for C. Okay, so what are we given? At time equals 5, the velocity is 0 and the acceleration is this. Now we've got the velocity function. V equals 9 over 4. V equals 9 over 4 plus B over t plus 1 whole squared minus ct squared. We are given that at time equals 5, the velocity value is 0. We can just input that here. 0 equals 9 over 4 plus 6 over 5 plus 1 whole squared minus ct squared. And that gives you, the value for t, what was that? 5. Okay, sorry, this was B. So that's a major blunder that I've done here. I wrote B here, and then I wrote that as 6. So you have to be careful about such mistakes. This is B. B over 9 over 4 plus B over 5 plus 1 whole squared minus C into 5 squared. Okay, let's simplify this. This is one equation that we're getting. 9 over 4 plus B over 36 minus 25c. That equals 0. This is one equation. We can multiply the whole equation by 36 so that the fraction gets eliminated, right? LCM of the denominators is 36. So I'm going to multiply everything by 36. That gives me 0 equals 9 into 9. That's 81 plus B minus 25 times 36. That's 900 times C. This is one equation that we're getting. Okay. Now, the other piece of information that we're given is that acceleration is minus 13 over 12 at that instant when time is equal to 5. So we can find the acceleration function. How do you find acceleration function from velocity? By differentiating. So let's differentiate this function and find the acceleration function from this. 9 over 4 is a constant. Its derivative is 0. What about the derivative of this? We can first of all write this in the proper form. Let me actually write it like this first. V is equal to 9 over 4 plus B into t plus 1 power minus 2 minus ct squared. Find the derivative of this. That's going to be acceleration. B into minus 2 into t plus 1 power minus 3 times the derivative of t plus 1, that's just 1, minus 2ct. That's the derivative. That's the acceleration function. We can simplify this first. A equals minus 2b divided by t plus 1 whole cube minus 2ct. Let's input values here. We can input t equals 5 and acceleration equal to minus 13 over 12. That's the point that they gave us. That will give us another equation. minus 13 over 12, that equals minus 2 times b divided by 5 plus 1 whole cube minus 2c times 5. Let's simplify everything now. We have minus 13 over 12, that equals minus 2b over 6 cube, that's 216 minus 10 times c. 216 divided by 12, yeah, that's divisible. So we can say 216 is the LCM. I'll just multiply everything by 216 to get rid of the fraction, right? What would that give us? 18, 13 into 18, that's 234 minus 234. So what I'm doing is just multiplying the whole equation by 216 so that the fraction gets eliminated. Minus 2b minus 2160 times c. These are two equations that I'm getting. I can divide by 2 to simplify everything. That will give me 117 on the left minus b minus 1080 times c. And since every term has a minus with it, I can just get rid of the minus as well. This is the other equation that I'm getting. Okay. Any problems with this? Is this okay until now? It looks like pretty big numbers, but let's just see what we get from this. Now we just solve these two equations. We have to find, we need to show that b equals 9 and find the value for c. Okay. In this case, since they're asking you to show that b is equal to 9, you could think of doing it like this as well, although it's safer to find it directly. And you only do what I'm about to say when they ask you for verifying something. But in this case as well, if it's like at the end of the paper and you don't have enough time, you could think of doing something like this as well. Put b equals 9 here and put b equals 9 here. If both of them are giving you the same value for c, number one, it confirms that b is equal to 9 indeed, and it also gives the value of c. So that will make it slightly quicker. That's something that you do when they ask you to verify something generally, we say. So if you do have time, then the better idea is to solve it like you would normally do. You make b the subject, and that gives you 900 c minus 81. And from the other equation as well, you can make b the subject if you want, and that will give you 117 minus 1080 times c. Equate these two equations and see what that gives you. 900c minus 81, that equals 117 minus 1080 times c. That's 1980c equal to 118 and then 198, and that will give you a value for c. That's going to be 0.1. Input that back in any one of those two equations to get the corresponding value for b. 900 into 0.1 minus 81, that's 90 minus 81, and that turns out to be 9. C is equal to 0.1 and b is equal to 9. And that's what you had to find in the first part. Any problems with this? Is this all right? Yes. Okay, let's move on. Now it says, given that the velocity of p is 0 only at t equals 5, find the distance traveled in the first 10 seconds of motion. Okay, so whenever they ask you to find distance traveled, normally what we have to do is we have to check if the direction is changing at any point. And how do you check that? By inputting v equal to 0. Now, in this case, we don't have to do that because they've already given that velocity is 0 when time is equal to 5. So that makes it simpler. All you have to do is, you've got the velocity function now, integrate that and input limits in that. You would have to do it in two parts, 0 to 5 separately and 5 to 10 separately, because the direction is changing at time equals 5. Okay, they've told you that velocity is equal to 0 at that point. So at that point, direction would change. You have to break your journey at that point. What's the velocity function? Velocity function is 9 over 4 plus b over t plus 1 whole squared. B was 9, so that's 9 over t plus 1 whole squared minus ct squared. That means minus 0.1 t squared. That's the velocity function. We can integrate this. See what that gives us. Integrate this. Integration of 9 over 4 is just 9 over 4 times t. Integration of this, let me actually write this in power form. 9 into t plus 1 whole power minus 2. 9 remains as it is. We add 1 to the power, divide by the new power, minus 0.1 t cubed divided by 3. That's what the displacement function turns out to be. If we had to find the displacement function, we would put plus c with this as well. But in this case, since we're just going to input limits, we would leave it as it is and simplify this and then input limits. How do you simplify this? It becomes 9 over 40 minus from here, minus 9, and that t plus 1 could go to the denominator, 9 over t plus 1 minus 0.1 over 3. We don't write this in decimals because, as in we don't simplify this because that's not going to be exact. 0.1 over 3, that will be 0.033333. You would prefer having it in exact form as it is. So this is the integration that we end up getting from that. Now we input limits from 0 to 5 in this, and then you input limits from 5 to 10, and that will give you the result. You have to make sure that you show the step in which you're inputting limits. That's important. You cannot write down the answer directly. That will not be acceptable. Minus 0.1 over 3 t cube. Input limits from 5 to 10 in this. Okay, let's do that for the first one. First of all, let's see what that gives us. When we input t equal to 5, that gives us 9 over 4 into 5 minus 9 over 5 plus 1 minus 0.1 over 3 into 5 cube. Subtract from this the case when you input t equal to 0. When you input t equal to 0, this term becomes 0. The second one does not become 0. That is 9 over 0 plus 1. The third term also becomes 0. This is what we get when we input these limits. Okay, now we can simplify this and see what that gives us. Let's figure this out. 45 divided by 4 minus 9 over 6 minus 0.1 divided by 3 into 125. Right? Yeah, I would recommend that you write this first separately. 67 over 12. That will help you in the next part because you will know the value at t equals 5 already. You can input that directly there. Then minus 9, that becomes plus 9, and that will give you something. That's 175 over 12. That's the distance traveled from 0 to 5, first of all. Okay, that's what we were looking for. Once we've got this, now we input limits for the second case. Input 10 in this one's 9 over 4 into 10 minus 9 over 10 plus 1 minus 0.1 over 3 into 10 cube. Subtract from this the case when you input t equal to 5. You already know what you get at t equals 5. You can just write that directly. That's 67 over 12. And figure out what this gives you. 2275 over 132. 2275 over 132. Okay, that's the displacement for the second part of the journey. Now we just add them up together. They're both positive. They're both positive. They're both positive. Okay, let's just confirm that as well, that the direction is not changing. If I input t equal to 0 in the velocity function, let me just check if the velocity function I have copied is correct. 9 into t plus 1 whole squared, 9 t plus 1 power minus 2 minus 0.1 t squared. Okay, now this was the velocity function. Now in the exam, if you are getting both positive, what that means is that both of them that you're moving in the same direction. You're moving in one direction throughout. Now, is the direction not changing? First of all, please verify the calculation. Abdul Rafi, why did you do that? Okay, so anyway, so in case you end up getting a so the actual answer is that you're now telling me is negative. Is actually negative. But if you end up getting both positive, that is possible sometimes. For example, think of a velocity function like this. Its velocity becomes 0 at this point. However, the direction still is not changing. It just came to instantaneous rest and then went back in the same direction. The velocity it remains positive throughout. So that is possible sometimes. Okay, so that is possible. In this case, however, you're saying that's not the case because this was actually negative. Okay, so that's all right. Then we say distance traveled. What does that turn out to be? Now you just add up all of these numbers, both of these numbers, 175/12 plus 2275 divided by 132, and that should give you the result. That's 31.8. Thank you. That's the final result that you get. That's the distance traveled. Okay. Yes, sure. You should definitely prioritize tomorrow's paper if you have one tomorrow. Okay, so that was part two of this. That's it. That's what we wanted to solve in this one. I wanted to find in this one. So these were three questions that you asked about from this paper. Question number 4, 6, and 7. Right? Okay. Let's go to the next paper now. Paper 4.1. So we started with 4.3 first of all. We did some questions from that. Now the next paper that you want me to do some questions from is paper 4.1. So from this, the two questions primarily are question number 5 and question number 7. Okay, let's do those two from this paper now. Question 5 and question 7 from June 22, paper 4.1, 5 and 7. Okay, let's have a look at this. Question number 5. Okay, so it says two racing cars A and B, they are at rest alongside each other at a point O on a straight horizontal test track. The mass of A is 1200 kilograms. Okay, so it's a horizontal track. Engine of A produces a constant driving force of 4500 Newton. When A arrives at a point B, its speed is 25 meters per second. The distance OP is d meters. The work done against resistance between O and P is 75,000 joules. Show that D is equal to 100. You got so many hints about what you're going to do in this question. They've talked about work done against resistance. They've given you the speeds, the driving force. Does that remind you of something? Work done by the driving force, that is equal to change in kinetic energy plus the change in potential energy plus work done against resistance. Whenever they talk about specifically work done against resistance and you have information about speeds, etc., this is what you have to do in those situations. You apply the work energy principle. The situation is like this. It's a horizontal surface and the car A that is going in one direction, its mass is 1200 kilograms. Okay, so they were at rest initially. So it starts from rest and it reaches a point here. At that point, its velocity is 25 meters per second. This distance is d meters. Let's just input values in this. What's the driving force? The driving force is 4,500. So what's the work done by the driving force? 4,500 times the displacement. That's the work done by driving force. That equals change in kinetic energy, half into m, that is 1,200, into v squared, that's 25 squared, minus u squared, that's 0 squared. Plus change in potential energy. There is no change in potential energy here. There's no change in potential energy. So that's just going to be 0. Okay, that's just going to be 0. Work done against resistance. What's that? That's given to be 75,000. Find the value of D from that and see what that turns out to be. 4,500 D, that is equal to 600. Okay, Abdul Rafi, let's talk about that after this question, okay? Okay, now the question says show that D is equal to 100. The answer is already given there. You have to show steps. You cannot write down the answer directly, okay? Whenever they ask you to show something, you have to be extra careful about showing every single step that is possible, okay? So in this case, you can do it step by step like this, as in just so at least one more step. Simplify this thing, 600 into 25 squared. What does that give you? That gives you 375,000 plus 75,000. Now after this, it is fairly straightforward. So if you want, you can write down the final answer after this. And that you're saying turns out to be 100. That's the value for D. Okay. All right, that's question number 5. Then it says car B starts off at the same instant as car A. The two cars arrive at B simultaneously and with the same speed. So they're starting at the same instant. They are ending at the same point as well. And it arrives at the same speed as well. Okay. The engine of B produces a driving force of 3,200 Newton and the car experiences a constant resistance to motion of 1,200 Newton. Find the mass of B. Okay. So what do we do? What do we know about this now? We've got car B that starts from here. This is the second car now. It is also traveling the same distance. What was that distance? That distance is 100. So it's covering a distance of 100 meters. And we know it's arriving at the same speed there, 25 meters per second. It also started from rest. The driving force is given to be 3,200 Newton. There is a resistance of 1,200 Newton. We can again just apply the work energy principle, work done by the driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. Work done by the driving force. But we are looking for mass, right? For mass, yeah. So we can find that from the change in kinetic energy. Work done by driving force, what would that be? Driving force is 3,200. So 3,200 times the distance, that's 100. That's the work done by driving force. That equals change in kinetic energy. That's half into m into v squared minus u squared. That's 25 squared minus 0 squared plus the change in potential energy. That's 0. Work done against resistance. This is not work done. This is just the force. So you have to be careful about that. This is 1,200 Newton. That's the resistive force. 1,200. What's the work done against resistance? 1,200 times 100. And that's going to give us the value for m. You can see what that turns out to be. In this case, it's okay to write down the value of m directly because it's not a show that question. You just have to find the value for m and you can do that here. Okay, what's the value of m that you get? What's the value of m that you get from the 640 kilograms? Okay, thank you. M turns out to be 640 kilograms from this. And that's our final result. That's part B. Again, fairly straightforward. We just have to input values and this like this. And the work energy principle. Okay, let's look at the next part. It says find the steady speed. Steady speed, what does that mean? Acceleration is 0. Right? Steady speed, it becomes stable, constant speed, which means acceleration is 0. If acceleration is 0, forward forces and the backward forces, they are supposed to be equal to each other. When its engine is working at the same rate as it is at B. Okay. Rate of work. Working at the same rate. What's that? That's the definition of power, right? Rate at which something is working. So they're saying whatever was the power at the point P, it remains the same later on as well. Power is equal to driving force into velocity. We know the driving force, 3,200. At the point P, we know the velocity at that point P as well. That velocity was 25 meters per second. We multiply these two, and that's going to give us the power at that point. You can see what that turns out to be. 32, 64, 64 plus 16, that would be 8,000. 8,000 watt, that's the power. 8,000, 80,000, 80,000. 80,000 watt, that's the power that we've got uh, for the car B at that point. Okay, now steady speed, that means acceleration is zero. We can use resultant force equals mass into acceleration. Since acceleration is zero, the right side is zero. It's a horizontal surface at which the car is moving. So we have a driving force and we have resistance. Driving force and resistance are going to be equal to each other. What are we looking for? We're looking for speed. Okay, so we use power equals driving force into velocity again for that. Power is the same. Power is 80,000 watt. That equals, we have to find the speed, right? So we want the driving force at that instant when the speed is constant. How do you find the driving force? In this case, the driving force and the resistance are going to be equal to each other. Do we know the resistance? The resistance is constant at 1200. They told us that. So that means df minus 1200, that equals 0. df equals 1200. You could just directly write df as 1200 as well, because you understand from the question statement it's steady speed. So the forward forces and the backward forces are going to be equal to each other. So you could directly say that driving force is equal to 1200. Input that here, and that will give you the corresponding value for the driving force. 80,000 equals corresponding value for the velocity. 80,000 equals 1200 times v, and that will give the value for v. You can see what that turns out to be. What's the value of v that we get? 66.7. Thank you. 66.7 meters per second. That's the velocity, that's the speed that we were looking for, and that's our final answer. Okay. Any problems with this? Any questions, anyone? No problems? Okay. Abdul Rafi, M1, the recent M1s, they are a bit lengthy. Sometimes they are very difficult to complete in time. So it's okay if you're not able to do some of them in time. As in, don't panic about it, because generally the threshold takes care of that, as long as you do not miss out on any question parts that you know how to solve. So the key is to not get stuck at any very complicated question in the middle of your exam. That is what makes people mess up their exam if they end up, you know, uh, trying to solve a very difficult problem in the middle. Mostly, that's that question that we've talked about multiple times. Questions involving both kinematics and momentum. Do not do some of those parts are still going to be easy. For example, if it's a three-part question, maybe one or two parts may be fairly straightforward for that. But then uh, there might be one part where they talk about some particles colliding, and then something happening after collision as well, or something, or there being another collision after that. And there's kinematics involved as well, along with momentum. Those specific parts, just make sure that you don't do them in the middle of the exam. And the other questions that you know how to solve, make sure that you try to save time on them. And then the questions that you're left with at the end, uh, just do as much as you can on them. You will, once you've done enough practice, I hope you've done enough practice, because that is what makes you save some time on the paper. that some questions that are very repetitive. For example, if I would just look at this paper, you'll find some questions that are, questions that you'll find again and again in past paper. For example, this is just by looking at what they're asking about acceleration and tension. It has to be just an application of Newton's second law of motion. You have to save time on this question. This question, it's a 6 mark question. You need to make sure that you get done with it in like 5-6 minutes at max. Save time on this question. So the questions that are repetitive, this one as well, it was not that difficult, just an application of work energy principle. Save time on these questions so that the bigger questions that you get at the end of the exam, generally, you have enough time left for them to be able to think about them. And the first time you read the question statement, so this happens a lot in mechanics that you have to read the question statement again and again. Make sure that when the first time that you read the question statement, mark everything that you might need later on. For example, the way I'm highlighting everything here now in the paper, I think they don't recommend that you use a highlighter, but use some colored pen. Do not use that for writing anything, but you can use a colored pen for underlining stuff, or just doing something like this. You can do it with a colored pencil as well, so that you don't have to read the question statement again and again to find some important information. You should have highlighted everything that you might need the first time you read the question. And the way I generally do it is that some information that is already given on a diagram, for example, in this case, you would look at this question statement and you would only highlight the parts that are not already there in the diagram. So again, you save time when you are looking at, when you're finding any important information. Most of it would be given in the diagram already. You only highlight the parts that are not given there. For example, in this case, there is nothing that is not shown on the diagram except that the forces are in equilibrium. So you would just highlight that part. Everything else is on the diagram, and that will make sure that you won't have to read the question statement again and again uh, when you're solving it to find any important information, because you would have everything highlighted like that. And the first time you read the question statement, read it slowly. It's very important to understand it correctly. Don't rush into the question. Don't start solving it right away. Uh, Before you have understood what they're asking about, always make diagrams. Diagrams are important. Do not make new diagrams every time. That's why I have been repeatedly telling you guys to always draw diagrams to using a pencil. Okay, so that when you're done with one part, for the next part, you can just erase some of those parts that you do not need and then edit them. Do not make new diagrams for every part. That will also save you some time. So these are something that I can recommend, but practice is the most important thing, so that when you look at the paper, you find some questions that are very similar to what you've done before. So you try saving time on them, so that the questions that are relatively more difficult, you have more time to think about them. Okay, I hope that helps. Let's move on to the next one. That was question number 5. Let's move on to the next one, question number 7 from this paper. That's the second question that you're asking about from this paper. Okay. Question number 7 is what you're asking about from this paper. Let's have a look at this now. The two particles A and B of masses 0.4 kilograms and 0.2 kilograms respectively, they're moving down the same line of rate of slope of a smooth plane. So it's a smooth plane. Their masses are given. There's no diagram given in this case, so you should be drawing your own diagram. The plane is inclined at 30 degrees to the horizontal. A is higher up the plane than B. When the particles collide, the speeds of A and B are 3 and 2 respectively. And the collision between particles, speed of A is reduced to 2.5 meters per second. Find the speed of B immediately after the collision. Okay, now how do you think about this? It's just a simple application of conservation of momentum. You've got an inclined surface, but that's probably not required here for now. Let's just think about the speeds of both the particles before collision and after collision. A has a mass of 0.4 kilograms. B has a mass of 0.2 kilograms. What are their velocities before? Before collision, they are moving at 3 meters per second and 2 meters per second, respectively. They're moving down. Both of them are moving down in this direction. In this direction. Okay, so for A, we can say the speed is 3 meters per second. A is up the plane, B is down the plane. This is 2 meters per second. After collision, what about after collision? After collision, what happens is speed of A is reduced to 2.5 meters per second. So that means it's moving in the same direction, just the speed reduces to 2.5. It becomes 2.5 meters per second. What about the speed of B immediately after collision? We can use conservation of momentum for this. Momentum before collision equals momentum after collision. Momentum before collision, that's 0.4 into 3. We're considering downwards positive, right? 0.4 into 3 plus 0.2 into 2. That should equal 0.4 into 2.5 plus 0.2 into VB. We can find the value of VB from this, see what that turns out to be. That's 3 meters per second. Thank you. That's the first part. That's fairly straightforward. Now, in the second part, they say, after the collision, when B has moved 1.6 meters down the plane from the point of collision, it hits a barrier and it returns up the same line of greater slope. B hits the barrier 0.4 seconds after the collision, and when it hits the barrier, its speed is reduced by 90%. The two particles collide again 0.44 seconds after their previous collision, and then they coalesce on an impact. Show that the speed of B immediately after it hits the barrier is 0.5. Hence, find the speed of the combined particle immediately after the second collision between them. Okay, now that's again that problem, kinematics, momentum. And these problems take time. So you need to have enough time at the end to be able to think about them properly. So let's draw that diagram now. We've got an inclined surface that looks something like this. We know the angle of this inclined surface. The angle is 30 degrees. And they told us that A is higher up the plane than B. So let's say this is A and this is B. Okay, no. So they're talking about after the collision. So the collision has already happened. And at that point, they are at the same position. All right. So there's no distance between them at this point, just after the collision. So let's just represent it like this. Anyway, I'll do that again. Okay, so let's say this is particle A and this is particle B. They're both together. Okay, when B has moved 1.6 meters down the plane from the point of collision. Now, after the collision, B was moving at 3 meters per second and A was moving at 2.5 meters per second. Now, B moves 1.6 meters down the plane from the collision, from the point of collision. It hits a barrier at that point. So there's a barrier here. And the distance until the barrier is 1.6 meters. Then it returns back. It hits the barrier 0.4 seconds after the collision. And when it hits the barrier, its speed is reduced by 90%. Okay, now let's think about this. What do we know about this journey for B before, after that first collision? B is moving downwards. We can say this is the positive direction for B. What information do we have about that? We know initial velocity for B is 3 meters per second. That's one thing that we know. We know the displacement. Displacement is 1.6. What else? They've given us the time that it hits the barrier 0.4 seconds after the collision. So it takes 4 seconds, 0.4 seconds. Can we find the speed of B when it hits that barrier? Final velocity, let's find that. Which equation connects these four things? S, U, V, and T, that's that equation. S equals 1 over 2 into U plus V times T, right? We can use that one. That connects these four things. 1.6 equals 1 over 2 into 3 plus V into 0.4. What do we get from this? What's the value of V that we get? What's the value of V that we get from this? Five. Okay, so it hits at 5 meters per second. Okay. It hits at 5 meters per second. Now its speed is reduced by 90%. What does that mean? If it was 100% before, 100% minus 90%, that's 10%. It becomes 10% of what it was before. So speed of B after collision, after hitting the barrier, what is that going to be? Five into 10% of that. You can say 10 over 100 or 0.1. That will be 0.5 meters per second. This is the speed of B just after hitting the barrier. Okay. All right. Now we need to find that was one thing that we had to show. We have shown that. The next thing that you're asking for is hence find the speed of the combined particle immediately after the second collision between A and B. Now, after B hits this barrier, what happens after that? B goes back in this direction. A is coming down. Now, while B was going towards the barrier earlier, A has already traveled some distance already in the downward direction. Right? A has already traveled some distance. How much distance has it traveled in the downward direction until this point? Can we figure that out? So let's consider the second part of the journey now. Initially, the distance between the barrier and the starting point was 1.6 meters. Let me actually just copy this diagram. So we'll just leave it as it is for now. Okay, so now after B hits the barrier, the situation is like this. That B is at this point, and B is moving up, and it starts going up at a speed of 0.5 meters per second. What about A? A would have already traveled some distance while B was going downwards. Let's find that first of all. So A was going downwards. What do we know before B hits the barrier? What do we know about A for that part? Before B hits the barrier. Let's find that part first of all. We knew that initial velocity for A, that was 2.5 meters per second. Just after that first collision, its velocity was 2.5. We don't know how much distance it travels. We know the time taken for B to hit the barrier. That was 0.4. So that's the time taken for them to hit the barrier. And that's it. Do we have any other piece of information? Final velocity, no. Do we have displacement? No. Do we have acceleration? Can we find acceleration somehow? Can we find the value of acceleration somehow? Let's think about this. How do we find the value for acceleration? Is it a smooth surface? Okay, so it's a smooth surface. That's one thing that we know. and there is nothing that is acting there. B is going here. Okay, so it's a smooth surface. If it's a smooth surface, what does that mean? What is the acceleration going to be? 10 sine theta, right? If it's a smooth surface, we know what the value of acceleration is. If weight is the only force acting, acceleration can just be written as 10 sine theta. Angle is 30, so it will be 10 sine 30. So it becomes 10 into 0.5, which is 5. For both the particles, this is the acceleration. However, for A is moving downwards. We are taking 5 here. If B is moving upwards, that will have to be taken as minus 5 later. But for now, let's just find the displacement for A from the starting point. Let's figure that out first of all. What's the displacement going to be? S equals ut plus half at square. We can use that. What do we get from this? U is 2.5 into t, that is 0.4, plus 1 over 2 into A, that is 5, into t squared, that's 0.4 squared. And that will give us some value for displacement. So we would know where exactly would A be after those 0.4 seconds. Let's figure that out. 2.5 into 0.4 plus 2.5 into 0.4 squared. And that's giving me 7 over 5, that's 1.4 meters. All right. So now we know that A has already traveled 1.4 meters when B hit the barrier. So A is somewhere here, let's say. And we know that this distance was 1.4 meters. And the remaining distance between the two particles, that is only 0.2 now. That's only 0.2 meters. Okay. So now B is moving in the upwards direction. It starts at 0.5 meters per second. What about the speed of A at this point? We would also have to find that now. From this point onward, let's find the speed of A. Can we find that? We can use V equals U plus 80. V equals U plus 80. This is before it hits the barrier, right? What would that give us? U is 2.5 plus A, that is 5. Into time taken, it took 0.4 seconds. And that gives us 4.5. That's the speed of A. 4.5 or 4.7? How is it? Is it 4.7? Have I input something wrong? No, no, no. I'm just finding the speed of A at this point, first of all. Okay, so you can do that directly as well. So I was actually finding the speed at this point first. Okay, so we have time given. We could actually do it directly as well if we wanted. And in fact, we might not even need that then, or do we? If we know the time taken, we could actually skip some of this working. So I did not remember that we had the time given as well. Okay, so we have the time given at the point they collide. Okay. So if we have time given for afterwards, we know the initial velocity for B, we've got the acceleration, we also know the time, we could find the velocities at that point directly without even finding the displacement. We actually do not need this 1.4 as well in that case. Do we or do we not? Let me think about it. 1.4. If we start from there, yeah. Okay, so I was actually trying to find that time at which they collide, but they've already given that in the question. So we don't need that. We don't need that time. They've already given that. We don't need to find that ourselves. So we could skip some of this working. We could make it more efficient. We could just directly find the speeds at which they meet each other. That makes it much simpler then. Because we don't have to find that time now. Okay. So we know, let's just consider directly, they collide after 0.44 seconds. Okay. So here we can say, let's find the velocity directly. Find the velocity at the point they collide with each other. Right? Let's find that velocity at the point they collide with each other for velocity for A. Which equation can we use here? V equals U plus AT. And that gives us V equal to 2.5 plus A, which is 5 into T, which is 0.44. And that you're saying is 4.7. Okay. So that's the velocity of A just before collision. What about velocity for B? That's also straightforward now, because we know the time. We don't have to find that ourselves. This is the positive direction for B. It's moving upwards. We know the initial velocity for B. What's that? That's 5, 0.5. We know the time taken. What's the time taken? It hit the barrier 0.4 seconds after the collision. I should have highlighted this as well. It hits the barrier 0.4 seconds after collision. And then the two particles collide again at 0.44 seconds. So how much time does B take to travel from the barrier to the point of collision now? 0.44 minus 0.4, that's 0.04. That's the time taken. What else do we know? We know acceleration. Acceleration on a smooth surface is 10 sine 30, the same as before. However, since we are considering upwards positive for B, its acceleration would be -5, right? Because the gravity is acting downwards. That's the value for acceleration. We can find the final velocity with this as well. What does that turn out to be? 0.5 minus, like this, plus -5 into 0.04. What does this turn out to be? It can't be 0.7. It started from 0.5. Minus 0.3 or plus 0.3? Is it minus or plus? It's plus, right? 0.3 meters per second. So it's moving in the upwards direction still. Okay. So this is the velocity that we're getting. This is the velocity that we're getting for the particle B. Earlier one was for particle A. This is for B. For A, we were considering downwards positive earlier. For B, we were considering upwards positive. So that means these are the directions in which they're moving. A is moving here in this direction, and that is at a speed of 4.7 meters per second. B is moving in this direction at a speed of 0.3 meters per second. And now we have to apply conservation of momentum. In conservation of momentum now, we have to consider the same direction positive. It depends on which direction we're taking positive. So in the previous, in this part, if you took downwards positive for B, first of all, I would not recommend that you do that. That will make you do careless errors. B started its journey up the plane. Consider that direction as positive, right? After it hits the barrier, it's a new journey that is starting, and it's moving in the upwards direction. You should take that direction as positive. Okay, but even if you take downwards positive, you will get the correct results eventually. But in that case, you would have to use U equal to minus 0.5 here. and you would have to use acceleration positive in that case, and that would work. U would also have to be negative in that case then, if you use the acceleration as positive. Okay, if U is positive, then acceleration has to be negative there. That's a bit counterintuitive, so I would not recommend that you take those directions positive. Mathematically, that works, but it'll confuse you. Momentum before collision. What's that? Mass of now for momentum, we have to consider the same direction positive for both objects. We can take any of them positive. For both objects, it has to be the same. So for momentum, now I can say, let's say this direction is positive. What are the masses? What are the masses? 0.2, 0.4, and 0.2. This is 0.2 and A is 0.4. Let's apply conservation momentum. Momentum before collision for A, it's negative velocity. So that's 0.4 into minus 4.7 plus 0.2 into 0.3 for B. That equals momentum after collision. After collision, the particles coalesce. And we have to find the speed of that coalesced particle. The total mass is going to be 0.6 into Vc. And that's going to give us the value for Vc. You can see what that turns out to be. What's this value? Minus 3.03. And that's basically telling us, the negative sign is telling us that it's moving in the downward direction. They've just asked for the speed, right? Speed cannot be negative. You would write the final answer as positive. You would say the speed of the combined particle, therefore, is 3.03 meters per second. Okay, and that's your final answer. That's what you wanted to find out. Is that okay? Any issues with this? No? Okay, let's move on to the last question then. This was paper 4.1. Now, let's do just one question from paper 4.2 that some of you asked about. Question number 4. Okay, paper 4.2. This is the last one. And this apparently is a relatively easier paper from the poll that it looks like it. Okay, June 2022, paper 4, variant 2. Let's have a look at some questions from this. In fact, just one question. Let me put this quickly as well. Question number 4. Let's do this one question from this paper, and then we end for today. A particle A moving along a straight horizontal track with constant speed 8 meters per second. It's a horizontal track, speed 8 meters per second, passes a fixed point O. 4 seconds later, another particle B passes O, moving along a parallel track in the same direction as A. B has speed 20 meters per second when it passes O. Four seconds later, another particle B passes O. It has a constant deceleration of 2 meters per second square. B comes to rest when it returns to O. Find expressions in terms of t for the displacement from O of each particle t seconds after B passes O. Okay, displacement of the particle A, first of all. T seconds after B passes O. Okay. So time is, t is the time for B. Okay. We've got A here, we've got B here. B starts later, right? B passes 4 seconds later. They're saying time for B is t. If time for B is t, the particle that starts late, we say that takes less time to reach the same point eventually, right? So if time taken for B is t, what about the time taken for A then? B's time should be less, right? A's time should be more. So A's time is going to be t plus 4, therefore. right? That should be t plus 4. Make sense? These are the values of t that we would be using in this case. Now, what about the displacement function for the displacement function for particle A? It's moving at constant speed. At constant speed, we can also just use displacement equals velocity into time. That's just 8 times t, 8 times the time. Time in this case is t plus 4. So we say s equals 8t plus 32. That's the equation that we've got for A. What about B then? B is moving at a constant deceleration of 2 meters per second square. What information do we have about this? At B, it has a speed of 20, so U is equal to 20. Deceleration is 2, that means A is equal to minus 2. And we have to write down the equation in terms of T. S equals ut plus half at squared. We can say 20t plus 1 over 2 into minus 2 into t squared, and that becomes S equals 20t minus 10 minus t squared. That's the displacement function for the particle B. And that's what you have to write down. Displacement of A and displacement of B. Make sense? That's the first part. Let's move on to the next one now. That's part A. Now it says find the values of t when the particles are at the same distance from O. Now, once you have these displacement functions, distance from O, what does that mean? Distance from the starting point, that's the definition of displacement. So they're saying find the values of t when the particles have the same displacement. Now we know the displacement function for both of them. Displacement function for A was 8t plus 32. Displacement function for B, that is 20t minus t squared. You just equate both of them, and that gives you 8t plus 32, that equals 20t minus t squared. That's a quadratic equation that we get. Values of t, so we are going to get multiple values. T squared minus 12t plus 32 equal to 0. We can see if we can factorize this. 8 and 4 will work. 8t minus 4t plus 32 equals 0. And that gives us two factors, t minus 8 and t minus 4. So t equals 4 and t equals 8. These are the two values of t that we're getting. This is when the displacements are equal. So that's the second part. That was fairly straightforward. Now it says on the given axes, sketch the displacement time graphs of both the particles for values of t from 0 to 20. Now, what are the displacement functions? The first one was 8t plus 32, I think. Yeah, 8t plus 32. And the second one is 20t minus t squared. Now, the first one is just a straight line. Just figure out the displacement at time equals 0. At time 0, the displacement would be 32. Let's mark that point somewhere here. Let's say this is 32. At time equals 20, you can find that. 8 into 20 plus 32, you should show these points, 192. Let's mark this here. This is 192. So you could say it's somewhere around here. Okay, you will use a ruler to make sure that it aligns with that. I can't do that here, so I'll just mark it like this. And that's the graph of the first function. This is displacement of A. What about displacement of B? That's a quadratic function. And what's the shape of this quadratic function? It's an N-shaped graph. It's going to look like this. Now, what part of this graph is going to be here? We can find the x-intercepts of this. Put s equal to 0. What does that give you? 20t minus t squared equal to 0. Displacement is 0 at 2 points. Take t common. T into 20 minus t equal to 0. And that gives you t equals 20 and t equals 0. So displacement has a value of 0 when time is equal to 0 and time is equal to 20. That means the graph has to start from here and it ends at here. At 0 and 20, displacement is 0. In fact, the question actually told us about this as well. I forgot that, I think. The question tells us that it comes to rest. Okay. This is the displacement time graph. Okay, so it comes to rest when it returns to O. Okay, that makes sense because the value becomes 0 at that. Okay. So these are the 2 points that we have, 0 and 20. Now, we have to make a graph like this, right? It's a quadratic graph. It's a symmetric graph. For a symmetric graph, the turning point is exactly between the two x-intercepts. So the turning point will be exactly in the middle. So at 10, you'll have the turning point. You can find the value for displacement at 10 so that you can show that accurately on the graph. What's the value of displacement when time is equal to 10? 20 into 10 minus 10 squared. That's 100. So at time equals 10, the value for displacement is going to be 100. So the graph looks something like this. Now, do they have any points of intersection? They have the points of intersection as well, right? They intersect when time is equal to 4, and they also intersect when time is equal to 8. So they intersect at these 2 points as well. At time equals 4 here, and at time equals 8 here, they will be intersecting. So there has to be a point of intersection here, another point of intersection here. So the graph would look something like this. You would say it looks like this. Looks like this on this side. It has this turning point when time is equal to 10. And similarly, on the right side, you make something like this. That's the graph that you're looking for. This is the graph for B. That's the part C of this. Is that okay? Any issues with this? So we had to show the x-intercepts at 0 and 20. The turning point was supposed to be exactly in the middle. The y value for that turning point is 100. And also, we found the points of intersection in the previous part. It was supposed to, and the graphs were supposed to intersect when time was equal to 4 and when time was equal to 8. So they intersect at those points as well, like this. Okay. All right, good. So that's the last question that we had, and we end here now. Tomorrow, you can come with any random questions that you might have. We will most likely start around 7 p.m. or maybe 7:30 p.m. We won't have the P3 class tomorrow. Those of you who take P3 as well, it'll just be M1, so we might be able to start a bit early. Maybe not 7, we might do it around 7:30 or 8. I will confirm that. I'll confirm the time. So if you have any questions tomorrow, you can come and ask those questions. It's not going to be a proper past paper class, as in we will not be solving any complete paper or any specific paper. You can come with your questions from anywhere. Uh, Make sure that you spend this time now from now onwards on revising everything, revise every concept. I've shared those notes with you in PDF form, the revision workshops notes. Make sure to go through all of them in detail. If you have any questions on that, you can ask them tomorrow as well. Have a look at all the questions that you have already practiced before in all the different past papers, especially the ones that you got wrong the first time. Have a look at them again. Make sure that you consolidate everything now, so that all the effort that you've done over the last few months, over the last year, you make sure that you benefit out of that now. So revise everything, have a look at everything again. And then if you have any questions, last minute questions, you can ask me about them tomorrow, inshallah. All right. All the best for your exam then. I'll see you again tomorrow in office.